Hello everybody, I'd like to talk about the factorial ANOVA and more specifically the three-way ANOVA, the 3x2x2, the unbalanced design. In the three-way ANOVA we have three independent factors. Each of these three independent factors has its own level, and regarding the unbalanced means that the observations in the groups of the experiment is not the same. I talked in a previous video regarding the balanced design. The question, we have this data inside this table, and this data comes from three independent factors, A and B and C. For factor A we have 3 levels, and for factor B we have 2 levels, and for factor C we have 2 levels. The needed is to conduct a three-way ANOVA on these data by hand calculations. Assume that the significant level alpha is equal to 0.05. So we have here the records or the data which comes from the experiment. Here we have the factor A, we have 3 levels. We have A1 and A2 and A3. And regarding the second factor, factor B, we have level B1 and level B2. And for the third factor, we have 2 levels, which are C1 and C2. Notice that the number of observations are not the same in these groups. So this is why this design is called unbalanced design. Before starting the calculation, let's understand and get more details from the question. We have the first factor, factor A. We have 3 levels. The first one is level A1, the second is A2, and the third one is A3. So small a is equal to 3. Small a represents the number of levels for the first factor, which is factor A. The second factor, we have 2 levels for factor B, which are B1 and B2. So small b, which represent the number of levels for the second factor or factor B, is equal to 2. The third factor is factor C. Again, it has 2 levels. The first one is C1 and the second is C2. So small c is equal to 2. Small c represent the number of levels for the third factor, which is factor C. So if you count for the combination between these 3 factors, simply you can multiply A times B times C, you will get a 12. So number of treatment groups or combinations between the factors is simply the multiplication of the 3 levels for the 3 factors, which is equal to 12. So we have 12 groups for the treatment. For example, in this main table, here we have this group, which represent group A1, B2, C2. We have 2 observations here, The two observations are 4 and 3. The total of the two observations is 7, and number of these observations is 2. For example, another example. This group here represent the group A3, B2, C1, and the records inside this group is 8, 9, and 8. So we have a total of observation, and we have number of observation, which is simply equal to 3. Capital N here represents the total observations. If you count for the total observation in the 12 groups, you will get 35 observations. So before starting the calculation, the first step to make the test for the three-way ANOVA is to state the hypothesis. For the first factor, factor A, the null hypothesis, H sub 0, states that the mean for A1 is the same as the mean for A2, is the same as the mean for A3, and the alternative one states that at least one of these three means is not the same as the other. For the second factor, factor B, again we have the null hypothesis, which states that the mean for B1 is the same as the mean for B2, while the alternative one states that they are not the same. For factor C, the null hypothesis states that the mean for C1 is the same as the mean for C2, and the alternative hypothesis states that they are not the same. So these are the sets for the hypothesis for the three main factors A, B, and C. Again, we have 4 sets of hypotheses for the interaction between these 3 factors. Regarding the interaction, we have the null hypothesis, which is always states that there is no interaction between the factors. While for the alternative hypothesis, it states that there is an interaction exists between the factors. For the 3 main factors A, B, and C, we have 4 interactions. The first one is AB, the second is AC, the third is BC, and the fourth one is the combination of the 3 factors, which is ABC. So we have 7 sets of hypotheses. We need to test all of these hypotheses. This is the three-way ANOVA table, and it contains the source of variation. We have the source of variation for factor A or main factor A, main factor B, main factor C, and regarding the interaction between A and B, A and C, B and C, A, B, C. So the total here is 7. And finally, we have the source of variation, which is the error. So we need to calculate the degrees of freedom for all of these. Then we need to calculate the value of the sum of squares as S. Then we need to calculate for the mean square MS. Then simply we can calculate the value of, and we will determine the value of the critical F and compare it with the calculated ones in order to make the conclusion. So we need to fill all of these cells inside this three-way ANOVA table. Let's start with the calculation of the degree of freedom. Degree of freedom for factor A is simply number of levels for this factor minus 1. We have 3 levels for factor A, so 3 minus 1 is equal to. For the second factor, factor B, number of levels, which is B, is equal to 2, so 2 minus 1 is equal to 1. The third factor is factor C, number of levels is 2, so 2 minus 1 is equal to 1. So these are the degrees of freedom for the main factors A, B, and C. Now we can simply count for the degree of freedom for the interaction between these factors. Degree of freedom between A and B is simply the multiplication of the degree of freedom for factor A times the degree of freedom for factor B. So 2 times 1 is equal to degree of freedom for A and C is simply degree of freedom for A times the degree of freedom for C, which is equal to 2. For B and C, this is the degree of freedom for factor B, and this is the degree of freedom for factor C, so the multiplication is simply 1. And regarding the degree of freedom for all the 3 factors, A and B and C, this is the degree of freedom for factor A, and this is for factor B, and this one is for factor C. So the multiplication yield the degree of freedom for ABC is 2. And regarding the degree of freedom for the error, we can simply use this formula, capital N, which represent the total number of observations minus A times B times C. So the total number of observations is equal to 35, while small a is equal to 3, small b is equal to 2, and small c is equal to 2. So the degree of freedom for the error is simply 23. Now we can easily calculate the degree of freedom total by summing up all of the calculated degree of freedom. For example, if you sum the 2 and 1 and 1 and 2 and 2 and 1 and 2 and 23, you will get the degree of freedom, the total, which is 34. Also, there is a simple formula to calculate for the total degree of freedom. Simply subtract 1 from the total observations, n. So 35 minus 1 is equal to 34. So this is the way how to calculate for the degree of freedom for the main factors, and for the interactions, and for the error and the total. Now simply we can fill in all of these degrees of freedom inside the three-way ANOVA table. Now the next step is to calculate the value of the sum of squares for all of these sources. But before starting the calculation for the SS, we need to calculate the correction factor. We need this correction factor in order to calculate for all of the SS. The formula for the correction factor is a very simple formula. Correction factor is equal to summation of y squared divided by capital N. Summation of y represent here the total observations, we square it, and capital N represent here the total number of observations. The total observation is already calculated. It is 189, and regarding the capital N, it is simply 35. So the correction factor is 189 squared divided by 35. So you will get the value of the correction factor to be 1020.6. Notice that all the calculated value is already filled inside this table at the corner. Now we can calculate for the sum square total or SS total. This is the formula for the calculation of the SS total. It is equal to the summation of the y square minus the correction factor. Summation of y square means the summation of the squared value of the observations or the records which are inside the above table. So what is needed to calculate for the SS total? Simply we need to square all of these 35 observations and make the summation. Then we subtract it from it the correction factor. The summation of the squared of the observation. We start with the first observation, which is 2. We square it, then we square the 3. Notice that 2 and 3 are inside this cell or this group. It is a group A1, B1, C1. So we have 2 observations. The first is equal to 2 and the second is equal to 3. So we make the square of these observations and summing them. You can easily use the Excel in order to get for these calculations. So the total or the summation of y squared is equal 1227. So now we can calculate the SS total. This is the summation of the squared of the observations, and this is the value of the correction factor. So we get the value of the SS total to be 206.4. So this is the way how to get the value of the SS total. Now we can calculate for the SS for the main factors, and we start with factor A. So we need to calculate the SSA. The formula to calculate the sum square for factor A is this formula. Notice that factor A has 3 levels. The first one is A1, so these calculations are related to the first level, and these second calculations are related to the second level, and this is related to the third level minus the correction factor. Let's understand the details of the calculation for the first level, which is A1 squared divided by n sub A1. A1 squared here means the summation of the observation for the level A1, and inside this table A1 here represent all of these observations. So if you calculate the summation of these observations, you will get 38. And if you count for the number of observation, you will find it to be 11. For example, here we have 2 observations, and here we have 4 observations, here we have 2 observations, and finally we have here 3 observations. So the total number of observations is equal to 11. Notice that all these calculations are filled inside this summary table. So for A1, we have a total of 38 for the observation, and we have the number of observation to be 11. The same for A2 and A3. Regarding A2, the summation of A2 is the summation of all of these records, which is equal 85, and number of observation we have here, we have 3, same like what we have here, 3, and here we have 3, and again we have here 3, so we have summation of 85. And regarding the number of observation n, we have 12. For A3, the summation of A3 is the summation of all of these observations, which is simply equal to 66. And regarding to n for A3, we have here 4. 4 and 2 is 6. 6 and 3 is 9. 9 and 3 is 12. So for A3, we have 66. And we have small n 12. So now we can substitute in the main formula for the SSA. This is A1, which is 38. We square it, divided by n sub A1, number of observations, which is 11. This is for A2 squared, and this is n sub A2. This is for A3, we square it and divide it by the number of observation, and we subtract the value of the correction factor. So simply you can proceed. You will get the value of the SS for the first factor A to be 75.76. The same way or the same technique we can calculate for the SS for factor B. This is the formula to calculate for the SSB. Notice that B or factor B has two levels. So these are the calculations for the first level, B1, and these are the calculations for the second level, which is B2. So what is needed? We need to calculate for the summation of B1 and the number of observations for B1 and the same for B2. Notice that in this summary table we have the sum of B1 is 88 and small n, which is the number of observations for B1, is 18. How we get these value? If we return back to the main table in the above here, B1 here represent simply all of these data. So if you make the summation for all of these data, you will get 88. And if you count for the number of observation, you will find it to be 18. So we have here 2, we have here 4, so 6 plus 3, 9, plus 3, 12, plus 4, we have 16, plus 2 is equal to 18. The same for B2. B2 represent all of these observations here. So the total of these observations is simply 101. And regarding the number of these observations, it is 17. So now we can substitute. This is the sum of B1. We square it. We divide it by the number of observation for B1. And this is the sum of B2 square divided by the number of observation for B2, and this is simply the correction factor, so you can proceed and you will get the value of SSB to be 9.68. Notice that as the value of the SS becomes great, the chance to reject the null hypothesis increase. So if you compare between SS for factor A and SS for factor B, you see that SS for A is significantly greater than SS for B. So the chance for factor A to reject the null hypothesis is greater than factor B. Okay, regarding the third factor, which is factor C, the same technique. For factor C, we have two levels. We have level 1, C1, and the second level is C2. So in this formula, these are the calculations for C1, and these are the calculation for C2. So for the calculation of the first factor C1, we need the sum of C1 and we need the observation related to C1. So in this table here, we have the summary of all of these calculations. The sum of C1 is 94 and number of observation for this factor or level is 18. So how we get the 94? From the main table here. C1 represent these data and these data and these data. So if you calculate for the sum of all of these data, you will get 94. And if you count for the number of observation, for example, here we have 2 and here we have 3, so we have here 5. If we had 3 and 3, we have 6. 6 and 5 is equal to 11. 11 plus 4 is 15. 15 plus 3 is equal to 18. The same way for the calculations of C2, we have a sum of 95 and N for C2 is equal to 17. Now we can simply substitute in the main formula for SSC. We have the 94, which is the sum of C1, we square it, and this is the number of observation for C1. And again, we have here for C2, we square it, and number of observation for C2 is equal to 17. And then we subtract the correction factor, so simply you can get the value of the SS for the third factor C to be 1.17. Notice the value of SS for the factor C is a little bit small, so the chance here to reject the null hypothesis is very small. By this, we count for the SS for the main factors A, B, and C. Now we need to calculate the SS for the interactions between the three factors, and we start with the SS for the factors A and B, which is SSAB. First of all, this is the formula how to calculate for the SS for AB. First, we need to calculate for the SS for the subtotals of AB. Notice that this is not SSAB. This is the SS for the subtotals between A and B, and we subtract the SSA and subtract SSB in order to get the SS for AB. How to calculate for the SS for the subtotals between A and B? The same technique as we have done. For factor A, we have 3 levels, A1, A2, and A3, and for factor B, we have 2 levels. So we have 6 combinations for factors A and B. Here we have the calculation for A1, B1. Here we have the calculations for A1, B2. And here we have the calculation for A3, B2. And finally, we subtract the correction factor. How to calculate for A1, B1, for example? In this table, here we have the summary of the calculation. So the sum of A1, B1 is equal to 20, and number of observation is equal to 6. How we get these value from the main table? A1, B1 is simply represent these values here. These values are the representation of the A1 and B1. So if you count for the summation, you will find it 20, while regarding the number of observation, here we have 2, and here we have 4. So small n for A1, B1 is equal to 6. For A2, B1, we have a sum of 43 and number of observation is equal to 6. A2, B1 is simply all of these records here, and the same way you can do it for the rest. So we have here 6 combinations. So simply we can substitute. For example, this is the sum of A1, B1, we square it and divide it by the number of observation for A1, B1. This value is the sum of A1, B2, we square it, and this is the n for A1, B2. And finally here we have the 41, which is the sum of A3, B2, we square it, and the number of observation is equal to 6. And finally we subtract the correction factor. So the value of the SS for the subtotal is simply 97.37. Now we can return back to the main formula to calculate the SSAB. So we have 97.37, which is the SS for the subtotals between A and B. This is the value for SS for A, and this is the value for SS for B. So the SS for the interaction between factor A and B is equal to 11.93. The same way to calculate the SS for the factors A and C, which is SSAC. This is the formula to calculate for the SS for AC. We need first to determine or to calculate the value of the SS for the subtotals between A and C, and subtract SSA and SSC. How to get the value of the SS for the subtotals? The same technique as we have done before. We need to calculate the interactions between the levels of A and levels of C. So we have 3 levels for A and 2 levels for C. So we have 6 combinations. For example, these are the calculations for A1, C1. These are the calculation for A1, C2. And finally, this is the calculations for the A3, C2. So let's understand how to calculate for A1, C1 regarding the summation and the number of observation. All of these data are inside this summary table. A1, C1, here we have a sum of 16 and number of observation is equal to 5. How we calculate for these two values? We can simply return back to the main table here. A1, C1. What is the meaning of A1, C1 from the main table? A1, C1 is simply all of these records or all of these observations. Notice that we ignore the value of for B1 and B2. So if you sum these 5 values, you will get 16. And we have here 5 observations, so n is equal to 5. Regarding for A2C1, A2C1 is simply these observations. So the total of these observations is simply 44, while number of observations is equal to 6. The same way for the other combinations between A and C. So now we can substitute directly. This is, for example, the sum of A1C1, we square it, divided by the number of observation for this combination, which is 5. The same way for the rest. And finally, we subtract the correction factor. So you can simply find the value of the SS for the subtotals, AC. This is not the SS for AC, this is the SS for the subtotals between factor A and C. How to find the SS for AC? This is the value of the SS for the subtotals. And regarding the 75, it is the SS for the factor A, and 1.17 is the SS for the third factor, which is factor C. So the value of the SS for AC is 7.11. The same way to calculate for the SS for factor B and C, which is SSBC. To calculate the SS for BC, we need first to find the value of the SS for the subtotals between B and C. Notice we have 4 combinations between B and C because B has 2 levels and C has 2 levels. So we have 4 combinations. This is the first one, which represent the calculation for B1 and C1. And this is the second one, which is the calculations for B1, C2. This is for B2, C1. And the last one is for B2, C2. For B1, C1, for example, we can simply get it from this summary table here. For B1, C1, we have the sum equal to 38, while the number of observations, it is equal to 9. How we get these two values? From the main table, B1, C1 represent simply these two values plus these 3 values plus these 4 values. So the total for all of these observations is simply 38, and if you count for the number of observation, you will find it to be 9. The same technique we can do for the rest of the combinations. So now we can simply substitute to get the SS for the subtotals. So the the value of the SS for the subtotal is 19.19. So this is the value for the SS for the subtotals between B and C. So now we can simply find the value for the SS for BC. This is the SS for the subtotals. This is the SS for factor B, and this is the SS for factor C. And this is the final value for SS for BC. Now, the rest is to calculate the sum square for all the factors A and B and C. So we need to calculate for SS, A, B, C. So first, this is the formula to get the SS for ABC. First, we need to calculate this unknown value, which is the SS for the subtotals between A and B and C. And we should subtract all the combinations, all other combinations, and all other SS for the three main factors. How to calculate for the SS for the subtotals for A and B and C? In this table here, for example, A1, B1, C1 is simply we have the sum for A1, B1, C1 to be 5 and number of observation we have 2. For A1, B2, C1 we have the sum which is 11 and number of observation we have 3. The same for the rest. Notice that to calculate for the SS for the subtotals, we should calculate for the 12 groups, simply because factor A has 3 levels and factor B has 2 levels and factor C has 2 levels. So we have 12 combinations. And finally, we should subtract the correction factor. Now simply you can substitute in the formula. This is the sum of A1, B1, C1. We square it, divided by number of observation for A1, B1, C1. This is the sum of A1, B2, C1. We square it and divide it by the number of observation for A1, B2, C1, and the same for the rest. And finally, we subtract the correction factor. So if you proceed, you can get the value for the SS for the subtotals. It is 161.9. So now we can simply calculate the SS for ABC. This is the SS for the subtotals. This is the SS between A and B. This is between A and C. This is between B and C. This is for A. This is for B. And this is for C. And this is the final value of the SS for ABC. It is 47.91. So all of the values for the three factors and the combinations have been done. Now simply we can calculate for the SS for the error. We calculate the SS total, and the SS total is simply equal to the SS for the three factors separately, and the SS for the combinations comes from the three factors or the interactions plus the SS for the error. So the SS for the error in this formula is the only unknown one. So we can move the known values to the other side. So we change the sign from positive to negative. So the value of the SS for the error is simply SS total minus SSA minus SSB minus SSC minus SSAB, SSAC, SSBC minus SS for ABC. So we substitute from the table in the above. So you can get the value for the SS for the error. It is simply equal 44.5. By this, we complete all of the calculation for the SS. Notice that almost most the time is consumed in the calculation of the SS. Now we can simply and easily calculate for the mean square, which is MS. The formula to calculate for the MS is simply to divide the SS by the degree of freedom. For example, for factor A, how to calculate for the mean square for the factor A, we simply divide the value of the SS for this factor by number of or the degree of freedom for factor A. So this is the way how to calculate for the MS or the mean square. For factor A, it is 37.88. For factor B, it is 9.68. For factor C, it is 1.17. For the interaction between factor A and B, it is 5.97. Between A and C, it's 3.56. For B and C, it's 8.34. And for all the three factors, it is 23.96. And for the error, this is the SS for the error, and this is the degree of freedom for the error. So this is the value of the MS for the error. We are interested here in this value, the MS for the error, in order to calculate for the value of F. How to calculate for F? Simply we divide the mean square by the mean square for the error. So for factor A, the value of the calculated F is equal to the mean square for factor A divided by the mean square for the error, and it is simply 19.63. For factor B, the value of the calculated F is 5.02. For factor C, it is 0.61. For A and B, it's 3.09. For A and C, it is 1.84. And for B and C, it is 4.32. And for A and B and C, it is 12.41. Notice that the larger the value of f, the highest chance to reject the null hypothesis. So we fill the value of the calculated f inside the three-way ANOVA table. Now the rest is to determine the value of the critical f. We can simply determine the critical f by knowing, first we should know the value of alpha, and alpha in our question is 0.05. We need to know the degree of freedom first for the enumerator and the degree of freedom for the enumerator, which is the degree of freedom for the error. So to calculate, for example, the f critical for factor A, we should return back to the f distribution table for the probability of 0.05 and degree of freedom 2 for the numerator and degree of freedom 23 in the enumerator. So this is the F distribution table for the 5%. So this row here represents the enumerator degree of freedom, which is simply the degree of freedom for the factor we need to determine the corresponding critical F. And regarding this column here, this column represents the denominator degree of freedom, and simply we have 23, which is the degree of freedom for the error. So the intersection between the 1 and 23 is 4.28. So the value of the critical F for alpha equals 0.05 and degree of freedom in the numerator equal to 1 and degree of freedom for the error in the numerator 23 is simply 4.28. The second value we need is for enumerator degree of freedom, which is equal to 2. And this is the degree of freedom for the error. So the intersection between these two values is 3.42. So the value of F critical for alpha equals 0.05 and degree of freedom 2 and degree of freedom 23 is simply equal to 3.42. We fill in these critical values of F inside the three-way ANOVA table, same like what we have here. So by this we finish filling all of the needed values inside the table. Now how to make the conclusion? It is very simple. We compare the calculated value of F with the critical one. If the value of the F calculated is greater than the value of F critical, So we conclude that we have a significance for this variable. For example, for factor A, the value of the calculated f is 19.63, and it is greater than the value of the critical one, which is 3.42. So we conclude for factor A that there is a significance, which means that for factor A, we reject the null hypothesis and accept the alternative one, which means that the value of the means for A1 and A2 and A3 are not the same, or at least one of the three is different from the other two. For the second factor, factor B, again we have the value of the calculated f is greater than the f critical. So for factor B, we reject the null hypothesis and accept the alternative one, which means that the mean for B1 is not the same as the mean for B2. For factor C, the value of calculated f is less than the critical one, so we don't have a significance here, which means that for factor C, we accept the null hypothesis, which means that the mean for C1 is the same as the mean for C2. For the interaction between A and B, the calculated value of f is less than the critical one, so we don't have here an interaction. So for AB, we accept the null hypothesis. And the null hypothesis for the interaction states that there is no interaction between the two factors, which are A and B. For the interaction between A and C, again, we don't have a significance. Simply the value of the calculated f is less than the critical one. So again, here we don't have an interaction between factor A and C, while for the interaction between factor B and C, the value of the calculated f is a little bit greater than the value of the critical one. So for the interaction BC, we reject the null hypothesis and accept the alternative one, which means that for BC, there is an interaction. And finally, for the interaction between the three factors, A and B and C, the value of the calculated f is significantly greater than the critical one. So for ABC, we reject the null hypothesis and accept the alternative one, which means that there is an interaction between the three factors A and B and C. So these are all the conclusions for our question. So to make a summary for the conclusion, we have only for factor A and B we have a significance because simply the calculated value of f is greater than the critical f, so we reject the null hypothesis, which means that there is a significance. For the interaction, only BC and ABC, the calculated f is greater than the critical one. So we reject the null hypothesis, which means that there is an interaction. While for the other factors, we don't have a significance, which means we should accept the null hypothesis. These are all about the three-way ANOVA or the factorial ANOVA. Please, if you have any comments, write it down. Don't miss to click the like and don't miss to subscribe in my channel. Thanks a lot and goodbye.